Good day, people, and welcome to our next visual lecture. Okay, for today's topic, we're going to talk about the phase diagrams. Okay, before I look into this particular chapter, so let's look at some of the chapter outline or the topics that we are going to cover in this chapter. We'll start with the definitions that are related to the phase diagram. And secondly, we'll look at the phase rule and also look at the two-component system, vapor pressure diagrams. We'll look at the temperature composition diagram. That will include the liquid-liquid phase diagram. And last but not least, we'll also look into the liquid-solid phase diagram. So if I still recall, ladies and gentlemen, I think some of these particular topics, we also covered them during the previous year. So if you can go back to your notes, I think you'll see that some of this stuff that we are going to cover here, they also exist in your notes. Okay, first of all, like I said that we're going to look at some of the basic definitions. So what is a phase? So when we talk about a phase, we basically talk about a state of matter which is uniform throughout, not only in chemical composition, but also in physical state. The key word in this statement is that something, it must be uniform. It must be uniform throughout, not only in chemical composition, but also in physical state. So this particular definition is very, very important. So when we look at the state of matter, we can have three different types of matter. We can have the solid state. We can also have the liquid state. And the other state that can also exist is the gaseous state. So looking at the solid state, we all know that the solid state can also exist in various phases. Like for example, like in the crystal structure, typical examples, they include diamond, they also include the graphite, or in compositions. And the solid state, they can also exist as the alloys. And typical examples of the alloys is whereby we are having a combination of more than one metal. So in case whereby we are having just one phase, we are going to say that P is equals to 1. So when we talk about the capital letter P, it means we talk about phase. So if you are provided with a statement and you are asked to calculate phase or P, we know what you are calculating. You have to look in terms of your reaction and to see how many phases you have. But if you only have one miscible phase, it means the value of P is equals to 1. But in case whereby you are having a miscible multiple phase, in that case, it is very obvious. The value of P will be greater than 1. For the liquid phase, even the liquid phase, just like the solid phase, it is possible that we can have the miscible liquids and we can also have the immiscible liquids. For miscible liquids, it's those type of liquids whereby we can only see one phase. Example is water. P is equals to 1. Immiscible liquids are those liquids whereby the value of P is greater than 1. A typical example in this case is whereby one can mix water and oil. We know that water and oil, they are not going to mix due to the difference in their densities. So when we look at that particular mixture, I think along the line, one is going to see here is a portion for water and here is a portion for oil. So in that case, we talk about the immiscible liquids. For the gases, a system consisting of gases can have only one phase. So in this case, the value of P is equals to 1. Because we all know that in the atmosphere, it is a combination of different gases. You can have oxygen, carbon dioxide, nitrogen, and others. And by our naked eyes, it is impossible that we can differentiate between those gases. Hence, we are saying that for the gases, the value of P is more or less equals to 1. So let's look at these two examples. The example on the left-hand side, I think we can see that we are having a mixture of sodium chloride. So when we look at that mixture of sodium chloride, I think we can see that we only have one composition of a liquid. So in that case, hence we can say that the value of P is equals to 1. Phase is equals to 1. But looking at the mixture on the right-hand side, I think from that class, we can see that we are having two phases. We can see that there is a bottom solution that is colorless, and the solution like on top of that glass that looks yellowish. So looking at that particular mixture, it is whereby we are having a miscible liquid. Those liquids, they cannot mix. So in that case, the value of P will be equals to 2. So here is another example. Let's say that we start with copper carbonate. So when we have copper carbonate, we're going to heat copper carbonate. So when we heat copper carbonate, we're going to convert it into carbon dioxide. And converting into carbon dioxide is going to release the gas carbon dioxide. So in this case, if we have to calculate the number of phases, the number of phases in this case will be equals to 3, which means we talk about copper carbonate, we also talk about copper oxide, and we also talk about carbon dioxide. So even when we sum them or when we add them, we see that the number of phase in this case, it is equals to 3. Moving forward, okay, let's look at some of the definitions before we can look at some examples. So within the system, we can have the heterogeneous as well as the homogeneous system. So what is the difference between these two systems? So when we talk about homogeneous system, we talk about a system whereby we only have one phase. But when we talk about the heterogeneous system, we talk about a system with more than one phase. Okay, except this heterogeneous and homogeneous system, there are also some definitions that are very, very important. I think these definitions, they're actually leading us to the phase rule. Because after this, these definitions, we'll be moving to the phase rule. There is what we call the constituent, and we also have what we call the component. What is a constituent? A constituent is a chemical species. It can be an ion or it can be a molecule which is present within a reaction. So if you are given a reaction, so if you have to calculate the constituent, it means that any molecule or any ion that is present within that reaction will be counted. All of them. For constituents, we are going to calculate each and everything that is present. It can be in an ionic form or it can be in a molecular form. So what about the component? So for the component is a chemically independent constituent of a system. So to calculate the component, we are going to say the number of the independent chemical constituent minus the number of distinct chemical reactions. So in other words, for us to be able to calculate the component, we need to know the number of the constituent. So even if the question did not say that we have to calculate the constituent, but if you want to calculate the component, it means we have to start by calculating the constituent first. And the formula, let us not forget this formula. It's the number of chemical constituents minus the number of the distinct chemical reactions. So in other words, if you are given one reaction and you want to calculate the component, it means it will be those component minus 1. There are certain reactions whereby they can occur in more than one ways, maybe 2 ways, 3 ways, 4 ways, or 5 ways. So if there are 4, it means for the number of distinct chemical reactions, we're going to put maybe the number 4. But here is another note. The number of independent chemical constituents is also equals to the total number of constituents minus the number of any restrictive conditions. Can be the charge neutrality or material balance, etc. But for this one, like if you are given like a statement or a reaction, from the reaction you'll be told that this is a restriction. So if you know the restriction, it means that formula of the component, it will be the chemical independent constituents of a system, or the number of independent chemical constitution minus like this restriction minus the number of distinct chemical reactions. I think when we move on with the examples, we are going to see how are we going to use these two formulas, or how are we going to calculate the constituents, and how are we going to calculate the component. Let's look at the following example. So in example number 1, we have calcium carbonate, which is in the solid form as the reactant. The product in that case is calcium oxide plus carbon dioxide. So if we want to calculate the number of phases, they must remember that when we talk about the phase, we said it must be uniform in chemical as well as physical properties. Calcium carbonate, we can see that we have a solid. Calcium oxide, we also have a solid, and carbon dioxide, and all those species, they're actually stable. They must be stable. Carbon dioxide is also stable. So in other words, the number of phases in this case, it is 2 for the both solid state plus 1 for the gas state, which means it will be equals to 3. 2 solid. 1 solid is for calcium carbonate, and 1 solid is for calcium oxide. So in other words, it is 2 plus 1, which will be 3. So here it becomes interesting. Let's say we want to calculate the number of components. Remember that I said that when you want to calculate the component, you have to start by knowing how many constituents are there in that reaction. The number of constituents, it means all the ions as well as the molecules that are there in that reaction. As you can see, we have calcium carbonate, calcium oxide, and carbon dioxide. It means we have 3 constituents. And how many reactions do we have? We only have 1 reaction. So in other words, for the components, it will be 3 minus 1, which will be equals to 2. So let's look at another example. So this one, it looks a little bit freak, but it's not difficult at all. Consider the system: sodium chloride, potassium bromide, and water. Suppose from that system, you can also isolate the following from it. You can isolate potassium chloride, which is in solid state, sodium bromide solid state, sodium bromide water, which is in the solid state as well, potassium bromide, which is in the solid state, and we can also isolate sodium chloride, which is in the solid state. So how many phases do we have like in this reaction? The number of the phases that we have, I think we have to look at our system. The first statement we are saying, consider the system: sodium chloride, potassium bromide, and H2O. Like sodium chloride, we are not sure whether it's in solid or liquid. Potassium bromide, we are not sure whether it's solid, liquid, or gas. But when you look at what we can isolate from that system, I think everything, it has been given. Potassium chloride, solid. Sodium bromide, solid. Sodium bromide water, solid. Potassium bromide water, solid. Sodium chloride water is solid. So in other words, the number of phases in this case, it will be P is equals to 5. 5 for the solid component. But what about the constituents? The constituents, I said that we look into our system, and in our system, all the ions or all the molecules that are present, they must be included. I think you can see that it is possible that the number of phases it is less than the number of constituents, because in this case, the number of constituents it is equals to 8. Why is it equals to 8? Because we have to count everything, whether it's in solid state or is not given in its state. So in this case, even sodium chloride, potassium bromide, and water, we are also going to consider them. So in other words, P, the number of constituents, is equals to 8. So if we know the number of constituents, it means we can calculate the components. Suppose that the following reaction it can occur in 4 different ways. The first way, sodium chloride plus potassium chloride, it will give us potassium chloride plus sodium bromide. The second reaction, sodium chloride plus water, it is sodium chloride water. The third one, potassium bromide plus water, it gives us potassium bromide water. And the fourth reaction, it is sodium bromide plus water, sodium bromide water. However, for this reaction, we have 4 different reactions that occur. However, we also have one condition. One condition is that material balance is the moles of potassium chloride, which is equals to the moles of sodium bromide plus sodium bromide water. So if we want to calculate the components, okay, let's just go a little bit on the previous equation. Remember that the equation was saying the number of independent chemical constituents minus the number of distinct chemical reactions. So as you can see from these reactions, the number of constituents in this case, it is equals to 8, and the number of reactions is equals to 4. As I said from the previous equation is that the number of independent chemical constituents is equals to the total number of constituents minus the number of any restrictive condition. In this case, we only have one restrictive. In other words, it will be 8 constituents minus 1 conditions minus 4 reactions. So the answer will be equals to 4. Okay, let's look at another example. And we must also remember that we must count the reactions which actually occur, not those which could occur. Let's consider a system. So in our system, we have the following. We have oxygen is in the gaseous form, we have hydrogen gaseous form, and we also have water that is in the gaseous form. So if the conditions are such that oxygen plus hydrogen that yield water, it does not occur. If the reaction can say calculate the number of components, but we are told that the reaction it does not occur. So even if we are going to calculate the number of components, remember the number of component is equals to the number of the constituent. The constituent in this case is everything in our reaction. We have oxygen, we have hydrogen, you also have water, which means the constituent it is 3. But so in this case, the reaction is not occurring. In other words, it will be 3 minus 0, which is equals to 3. Therefore, C is equals to 3. So if conditions are such that, like when we introduce the catalyst, oxygen and hydrogen will give us water, it occurs. So if the question can say that, what is the number of component? Because in this case, we are told that this reaction now, it will occur. If it will occur, just like the previous example, it means the value of C is still equals to what? It's still equals to 3. But in this case, we have a reaction. So in other words, it is C is equals to 3 minus 1, which is equals to 2. So if conditions are such that when the catalyst is introduced, hydrogen, it will yield water or gas. However, in this case, you impose the condition that all the hydrogen or oxygen, they come from the dissociation of water. So what will be C in this case? C in this case, it will still be 3 constituents minus how many reactions do we have? We still have 1 reaction. But in this instance, we also have another condition. So that condition will be subtracted. In other words, we have 3 minus 1 minus 1. So which is 3 minus 2. 3 minus 2, it is equals to 2. The most important thing that you must remember is that you must identity of component is a matter of some choice. Numbers is indeed. So you have to choose the components that cannot be converted into one another by reaction. I think, ladies and gentlemen, for this lecture, I'm going to pause at this slide. So during the next lecture, we'll start from the phase rule. I thank you for your attention. Thank you.